Okay, good morning friends, and this is
both lectures combined.
all 4 lectures combined, yes. So, today we will continue the recursive robot dynamics, and I wanted to emphasize here whatever the contents presented to you in last 2 days particularly on parallel manipulator closed loop system. They are very latest topics, and if you find it difficult, try to understand the philosophy first. Okay. And then if you go back and sit down, you should be able to derive it, okay, rather than understanding the maths immediately in the classroom. And as I put it here, they are taken from these 2 PhD thesis converted to books basically, and the one in the bottom, it has its Indian edition now, dynamics and balancing of multi-body systems, and the one in the top, the international edition is only available at this moment, dynamics of tree type robotic system. This algorithm okay, here. So, this is, so I just have to run. So, it has several folders here. So, what I am doing is I am trying to get the data related to forward linkage. Okay, this is the reducing module. I want to do forward dynamics for fixed base, forward dynamics, and then I have for the forward linkage. Okay. So, select folder. Okay. So, okay. So, I take all this data which is sitting here for your demo purpose and copy, I go there and I just paste there, yes to all, and then there is a file called run m. Okay, so this is there. So, now it will run for you, then simulation will come. Okay. So, in this case what happened is I did not put any external torque, I just let the forward linkage fall due to gravity. So, what you see is the free fall simulation here, and all those plots are corresponding to the joint positions, joint velocities, energy, so on and so forth, because I wanted to check whether my results are correct or not, and since there is no friction considered. So, I can check the energy input and then what energy I am getting it from forward simulation, how much error it is introducing. So, those studies we are doing it through those plots. Okay. So, that is very classical way of doing forward dynamics, but then here I will just for the sake of completeness, because cut open has the advantage to reduce the problem size. So, I will show you one such approach, what we call is a system level Lagrange multiplier method, that is the name we are using it. Now, what we are doing is again we are writing those 2 sets of equations for the first subsystem and the second subsystem. Okay. And now, we are this one, this block here we call it a I matrix. So, here, so this portion we will call it a I matrix, and this portion is J matrix, and then obviously this becomes J transpose. Okay. So, in the next slide I did exactly this thing. So, I 3 by 3 matrix I have defined by combining these 2, and then I have defined here J, okay, and then rewritten the whole expression in the previous slide. So, this I now contains 3 by 3 information. So, one subsystem 2 by 2, another subsystem is 1, and now here what I am doing is, instead of calculating theta double dot and lambda together through this linear algebraic equation, I wanted to calculate lambda first, okay, and then I will substitute this lambda in this equation just like we do in our school level, with a scalar equation. I am doing the same thing with a set of vector equations, okay, and I will see how the size of the problem is reduced. Let me show you how to get that lambda. So, I have I J transpose J 0, I have theta double dot lambda is equal to phi 0. Okay. phi contents are the velocity terms, external torques, etc., etc. So, all are hidden inside. So, now I write I theta double dot plus j transpose lambda is equal to phi. So, from here I can calculate theta double dot is equal to phi minus j transpose lambda into I inverse. This I has always inverse because I contains the system inertia and this is always symmetric, not only symmetric, it is symmetric positive definite. So, now this theta double dot I put it in the second equation. So, theta double dot is equal to 0. So, j I inverse phi minus j transpose lambda is equal to 0, and from here I calculate j I inverse j transpose lambda is equal to j I inverse phi. From here lambda expression I can calculate as j transpose, which I am giving in a name I bar inverse j I inverse phi. So, this expression of lambda will substitute back in this equation here. So, now this will become I inverse phi minus I inverse j transpose, I have I bar inverse j I inverse phi. Okay. Now, if you do little arrangement here, then the final expression would appear as you see it in the last expression, that theta double dot is equal to identity matrix minus j transpose I bar inverse j, okay, and phi bar. So, now if you look at the next level, next I again in a similar manner I integrate joint acceleration to get the joint velocity and position. Okay. Only thing is that this lambda I have avoided the explicit numerical evaluation which I have done in the previous step. So, finally, you see even in the previous slide I had to do this inversion here. Okay. So, here in this methodology I had to do an inversion of a 5 by 5 matrix, but here what is the maximum size I am inverting. Let us see what are the inversion coming. So, here one inversion is coming here. So, one inversion is coming here and that I is appearing here. So, this is 3 by 3, okay. And then I bar size, what is the I bar appearing here? I bar is the whole thing and this whole I bar will be 2 by 2. Okay. So, instead of inverting a 5 by 5, what I am doing it here, I am doing a inversion of 3 by 3 and 2 by 2. Okay. So, if you invert a 5 by 5, so the order of computation as I mentioned in one of my earlier classes, order n cube, that means order 5 cube. Here it will have order 3 cube plus 2 cube, which would be more economic than a computation of order 5 cube. 5 cube means 5 into 5 into 5, 125. Okay. Whereas 3 cube, 3 into 3 into 3, so 27 plus 2 cube is 8. The 27 plus 8 is 35. So, you are comparing something order 35 versus order 125, which is much more economic. And then as I mentioned in my first class, that other than efficiency, there will be issues of the numerical stability and so on and so forth. So, that was the story about the 4 bar linkage. I have told you the inverse dynamics, the forward dynamics, classical way, and then one approach system Lagrange multiplier method, because what we have done it explicitly we have found an expression for lambda, substitute back. So, that finally, I get a set of ordinary differential equation. Here I wanted to just mention bypassing this kind of formulation is called the DAE formulation in forward dynamics. Here what is the meaning of DAE? Differential algebraic equation. The first set of equations are differential equations and the last equation is coming from the position constraints A 0 plus A 1 plus A 2 plus A 3, and I have double differentiated it to get this expression, right. And these kind of equations for numerical solution there are challenges actually, because as if you are dealing with apple and oranges in the same box. So, one may go bad in time, maybe in 2 days time, another may survive for 7 days, but since they are together they may go bad poorly together on the 3rd day or the 4th day actually. Okay. So, that is the kind of things happen. So, to avoid that kind of problem, now what we have done it here, the last set of equation we have converted into ordinary differential equation by substituting back all those expressions. Okay. So, now next set of examples are basically the philosophies are presented, no detailed mathematics would be given. Next, look at 5 bar 2 degree of freedom planar manipulator. So, I have 1 bar, 2 bar, 3 bar, 4 bar and the base is the 5th one. So, 5 bar. So, if I use the cut method, the immediate approach would be let us cut it at the middle. Okay. So, I cut it at the middle, this scissor symbol means the cutting. So, I cut it here, but as soon as I cut it, now we have to replace with a some Lagrange multiplier which you call it. Now, this is equivalent to saying that that force is trying to bring them together, Okay. And so, this has a 2 degrees of freedom, you require 2 drive motors if you consider it as a manipulator. So, for the first subsystem I have this equation. How many equations of motion will come, because it is a 2 link planar system. So, 2 equations of motion will appear here. The second one here, how many unknowns if I want to do inverse dynamics. So, one of course, the driving torque I have to calculate tau 1 and this lambda has 2 components. So, tau 1 lambda x lambda y. So, 1 2 3 unknowns, but I have 2 equations. So, I cannot use these 3 unknowns to be solved from these 2 equations. So, I have to take the help of the second set of equations. So, it has a 2 equations, but effectively 1 unknown, because 2 unknowns if I assume that they are calculated they are same. So, effectively if you total them up, so 2 plus 2 4 equations and 3 plus 1 4 unknown. So, now I can combine them and solve them. Okay. So, this is not a subsystem approach which I told you, that you solve one subsystem and then getting the results of one subsystem you go to the second subsystem. So, in this approach subsystem recursion is not possible. What we call it here is a system, that means total system is combined together. If you have to take a subsystem approach, then a cutting has to be done in a different location, okay, which means what? I have to get a subsystem whose number of equations of motion should be equal to the number of unknowns corresponding to that subsystem. So, this is one such possibility that you cut it here now. Okay. So, now this will be replaced by lambda. So, in the right hand side 1 2 3 links. So, it will give rise to 3 constraint equation, which is the first one. So, 3 equations, how many unknowns? Tau 1 is unknown and lambda 2 components are unknown. So, 3 equations are unknown, right. Sorry, 3 equations, 3 are unknown. So, now these can be solved to find out all those unknowns. In the second subsystem 1 meter, 1 meter, 1 meter, 1 meter, very long, this is for the sake of simulations or the numerical results only. Mass of the links 6 kg each, and this is the plot you will get it for given trajectory of your active joint. So, here we presume this is an active joint, this is an active joint, means motors will be placed here to drive this system. So, this is the result will be coming. So, that means if you move it in a planar way on a system 1 here. So, what we do now, we cut it here. So, this is the cutting joint here and another is cutting joint here. So, I have shown you now this is my subsystem 1 after cutting. Okay. So, it has one chain 3 link system. So, 1 link, 2 link, 3 link system, and then there is a branching here. Okay. So, total how many degrees of freedom it has? It has 5 degrees of freedom, okay, because 5 revolute joints would be present there. If you use Groupless criteria formula, you will get it. So, subsystem 1 has 5 constraint equations of motions using our DNOC for example. Which are the unknowns? So, one is driving torque at this. Typically, this kind of parallel robot will have driving mechanisms here, motors, another motor here and another motor here. So, here this is the driving torque unknown, and I cut it at 2 locations. So, at this location I have lambda 7 and here I have lambda 2. So, lambda 2 has 2 component, lambda 7 has 2 components. So, 2 2 4 plus 1 5. Okay. So, you get these 5 unknowns solved from these equations, knowing lambda 2 and lambda 7. Now, this becomes known quantity for my subsystem 2 and subsystem 3. This is my subsystem 2, subsystem 3, and then effectively they would have only one each. Okay. So, again for this set of numerical values for different lengths and their masses, we can again run this program using Redisim. So, I run Redisim, I open in this, okay, and then this is related to 3 RRR. So, I have set of files, I just cut it from my directory there and bring it to the main folder, takes care of all the input data and everything, and then I run it, and then you will see, you see, oh, forward dynamics have come. This is the forward result. Let me show the inverse first. This is forward, forward, forward. So, I wanted to do inverse first. So, 3R, copy, paste, and then run